lecture with short form Cleotilde Gonzales, Carnegie Mellon, and also very happy to see people from very different areas in science and research. The topic, Adaptation to Change, is obviously extremely important in a world that is changing. And it's one of the core topics also for, I'm from social science, dynamic decision problems, detecting the change, deciding whether you should adapt to that change you've detected or not. The new developments with artificial intelligence, the merger between humans and machines, who decides what, how, what is a good division of labor between the two. Enormously important topics. I will not bore you with more random comments regarding that, but rather welcome Coty, and thank you so much for giving a lecture here.
Yes, thank you. Thank you everyone for being here, and I'm particularly grateful to Davide for inviting me. So it's my first time in Denmark, my first time here, so I'm really excited and hopefully not too jet lagged. And I'm happy to be next to other Einstein too. So that's great. And I didn't get my bag in my flight, so I'm adapting to change. Sorry for the more informal presentation today. So Davide told me it's okay, it's an informal audience. So the topic today is indeed quite broad, adaptation to change. Let me start with this quote, which is assigned to Charles Darwin. It is not the strongest of the species that survives, not the most intelligent that survives. It is the one that is most adaptable to change. And of course, he meant in the biological sense, but this quote, I think, applies to adaptation in the social way, in the decision-making way. So adaptation to change is probably the most important tool we have to deal with environmental changes. There are different systems that we have to deal with in our lives, and some systems change more slowly and others change faster. Climate change, for example, is occurring over many years, centuries, right? But it's in constant change. Climate is in constant change. And we are seeing a much rapid development lately because the change is not linear. And in every disaster that we know of, the change is usually not linear. It starts slowly, and then it becomes a lot faster. There are other environments in which the change occurs really fast. For example, in the stock market. A split of a second decision might make a difference whether you earn something or not, right? So you need to be constantly aware of change and be ready and prepared to adapt quickly. So these are the two questions that have indeed been in my mind for many years. So how do we adapt to changing conditions of the environment? And how do we contribute through the decisions we make to that environmental change? So those are the main questions that I address in my research. And that's why I started to look into something called dynamic decision making, a field that is less common than other type of decision making. Let's call it static decision making. So there is a recent review, by the way, that just came out on research and literature research on dynamic decision making. These are enlisted are the characteristics of every dynamic task. And I use the driving as an example of dynamic decision-making environment because that's something we all do or we know how to do. So in dynamic situations, the most essential element is that there is a series of decisions. So it's not a one-shot decision. Rather, we learn from the decisions we make. So there is a series of decisions. The decisions are sequentially interdependent. That is, the outcome of one becomes an input of the next one. In the case of the driving, if you have decided to turn right, you have a different situation than if you had decide to continue straight in your driving. So the output of your earlier decisions become part of your new environment. The environment changes exogenously, independently, but also dependently on your situation. You can think of traffic, weather being conditions of the environment that are present, but also the decisions that you make present the different environments. So it's interdependent change as well as exogenous change. And the utility of this decision is time dependent. This is important because time has not been considered as part of utility functions often. But indeed, it's very relevant. So you can think of pushing your brake when you have already hit the person in front of you. That's not very useful, right? So the time of the decision is very important. And there is always limitations of resources. Time is one of the resources indeed, but there are many other resources. So in dynamic decision making, there are different types of decisions also. So the first one I'm showing here today is consequential choice. By consequential choice, driving is one example. I mean, you cannot help but adapt to the decisions that you already made. There is no way back, okay? So same thing in the stock market, and the most common example is actually firefighting. So a lot of the research on dynamic decision making in the early 60s, 70s was actually done through firefighting and investigating firefighters in action. So once you made a choice in that case, you cannot go back. You only can move forward and adapt to the choices that you have already made. Okay. But there are also other types of dynamic decision making. For example, what we call choice from sampling. So in this case, when you go and buy clothes, we can think of them as less consequential than firefighting too, but it's also dynamic in the sense that the order in which you look at your options is going to determine what you are going to select later. It's going to determine your choices. Ice cream, speed dating. The order in which you see your options is going to determine what you are going to select later. And housing, of course, if you make an offer in your house too late, you are going to lose the house of your dreams, right? So the order and the timing of the decisions is again very important. But the characteristic of this type of dynamic decision making is that you explore the options first and then you make a choice. You are not committed to the options as you move along, okay? There is yet another type of dynamic decision making that I call control. An example of that is climate change, which is an extremely complex system. But to make it, to give you a simpler example, in our health, we are continuously making dynamic decisions. So for example, we have to balance our weight and our exercise, what we eat and how much we exercise, because we want to keep a balance. So what is important in this type of decision making is it's not about maximizing utility, it's about control. It's about keeping things in balance. Diabetics do this all the time. They need to figure out how much to consume, if they are using insulin, how much insulin to inject to be able to balance the level of sugar in their blood. So this is extremely important, and it's also dynamic decision making.
Sorry, just
yes.
In case you don't tell Trump that. But what was the point about the climate change? What was the problem there? I mean, as a sample, I actually missed the point.
It's simply another an example of a control type of decision making. It's a very complex system where there are many variables and they interact with each other. So I jumped immediately to a simpler system, which is obesity in this case.
I should be very clear that there is no misunderstanding with climate, right? Has to be fixed.
What do you mean by have to be fixed?
In the sense that it should not come as a message that there are too many variables, therefore we don't know what to do.
Oh no, that's absolutely not the case.
Okay,
Yeah, and in fact,
just because you know.
no. It's a very complex system, yet it is a dynamic decision-making system. And we can talk if you want. I don't have a lot of that work in this, but
I just want to make sure that there's no misunderstanding. Scientists are completely agreeing that only one way to go, is to reduce CO2, and anything else.
There is no
really
question about it.
Yeah, there's,
No
I want to
question
avoid the
about it.
Trumpian, not yours, potential Trumpian attitude.
Yeah, no
Going
question
denial,
about it.
right?
Okay, so an important thing of these three categories of dynamic decision making is that, at least initially, all these researchers from different fields and areas work or concentrate on the environment, so characteristics of the environment. The environment can be seen as belonging to different disciplines, but one important characteristic that matters here is complexity. So initially, looking at structural complexity, meaning a number of elements, the more alternatives you have, more attributes, like in the case of the climate change, there is a more complex system than, let's say, the obesity problem, right? So complexity, structural complexity in particular, is important, but also dynamic complexity, and this is often studied much less than structural complexity, meaning a system that is very simple at the structural level can be very complex dynamically. It can have only two elements, but the way those elements interact over time makes the system very complex. I have some examples of that. By the way, I'm afraid that my presentation might be longer than the time I have, so whenever I have to cut, I will have to cut, or if I go too fast, stop me. I'd be happy to cut it whenever I have to cut it. Okay, so what I realize is that there are degrees of complexity. So there are some systems that are extremely complex, some systems that are simple structurally, and that these dimensions vary, right? So you can study systems that are very complex or simple, but even in the very simple structural systems, there is a lot of complexity. So in my initial life of research, I worked with microworlds and video games to represent naturalistic situations in laboratory tasks, simulations. So these are some of the examples of the simulations that I use. Actually, I have one that was a dissertation of one of my students on climate change. And all of them have these characteristics of dynamic decision making. I'm happy to talk to you more about them. But there was this one here in particular, that was the source of most of the theoretical ideas that came in the early 2000s. So that's called the water purification plant. There's a long story behind this task, but I'm going to try to make it short. Essentially, it's a dynamic resource allocation task in which the operator plays the role of water purification plant controller. And you have limited resources. You can only have 5 pumps that can be turned on, like in this case, at the same time. You can think of this as there is simply not enough energy to run more than 5 pumps. And as you see, you could turn on many pumps, 66 to be exact. So you have to distribute your limited resources in a way that is optimal, so that you can purify the water of the system before different deadlines, okay? As you can see, the deadlines are not organized in any particular way. The earliest is 5 o'clock. So if you think that a simulation starts at minute 0, at 5 o'clock, you need to have these tanks that lead to the 5 o'clock deadline empty. That means you have processed all the water of that chain on time, okay? So the water is moving. I don't know if I have time to look at the video. Actually, I'm not going to go through that. But you can look at the task in real time moving. The task goes from 0 simulation time to 10 o'clock, which corresponds to the last deadline. So your goal in this task is to distribute all the water on time. So that means the optimal performance would be what? Have a guess? Well, how do you know if you did well as an operator of this plant? Okay, I'll make it easier, sorry. It would be if you have processed all the water on time. That is, if you don't miss any buckets of water. So your optimal performance in this task is 0, okay? So that you get an idea, if you do absolutely nothing, if you just put your hands back and you don't make any decision in this task, you get 1,008 buckets of water missed. That's the worst performance if you do nothing, right? So anything that you do is supposed to reduce your performance, reduce your score, meaning to do better. You have better performance. Okay, so I bring this task because again, this is an old experiment, but this is the source of the theoretical ideas that I'm gonna present later. Some of the questions I had was, if practicing this task, if I do this task many times, do I become better? So there was the idea in dynamic decision making that practice does not make perfect. Is that true? So that's one question. The second one is practice under time pressure help perform under time pressure. So the military who gave me money to do this type of experiments were interested in how to train their soldiers. So soldiers need to be under time constraints and a lot of stress. Do I need to train them on the same conditions so that they perform well in the field? And that's the other question, right? So for that, I ran an experiment that was over 3 days. So in the old days, we ran these experiments that we ask people to come back to the lab. I don't do that anymore. But in this case, it was 3 days. In the first 2 days, we provided training to the participants in 2 conditions, the fast condition and the slow condition. The fast condition means they run these tasks that I just showed you, the WPP, 6 times at a pace of 8 minutes. That means each simulation the time was concentrated into 8 real minutes, okay? And they run it 6 times, and they did the same in the second day. In the slow condition, they only run it 2 times, but a lot slower. So the time within the simulation was moving more slowly, okay? 24 real minutes. And then in the third day, they all came back to run exactly the same task. 6 times 8 minutes, like the guys that did it at the fast pace, okay? So we also were interested in some cognitive characteristics from the participants. So what helps people do better? What type of cognitive abilities? We had already used a lot of memory tests and all that, but in this case we used the Raven Progressive Matrices test. Who's familiar with that? Raise your hand. Okay. So this is an intelligence test. It's a G test, General Intelligence Test. And it's a long test. It's a 60 questions test, but we used a shorter version, and this is one of the questions from that. Essentially, what this test measures is our ability to pattern match, our ability to find patterns. So in this case, this is the overall pattern, and you are presented with options here. And you have to complete this matrix by selecting one of the options. So what's the answer in this case? Anybody? 6. So if you put this pattern here, that would complete this pattern. And like this, there are 60 questions. Of course, some questions are more complex. So the idea is that these tests help you look at the different relationships between the figures, the columns, the diagonals, and then figure out what is the right answer. I'm not gonna ask you which is the answer here, because I myself had a hard time figuring out. So it is number 5. But you know, the questions go from easy to harder. And the point is that we were interested in this to be able to relate to the performance in that task and figure out if indeed pattern matching is an ability that people need to have, all right? So here are some of the results, and in this case, remember that 0 is better, all right? So these are the overall performance of fast and slow. Those that were run in the fast condition, this is what they perform, and I just sort of highlighted the last day to remember that they all are doing the same thing on the third day. So as you can see, the people that run it in the slow task, they improve their performance, and they continue to improve after they were put into time pressure. What this means is that slow is fast. So you can adapt to time pressure if you are trained without time pressure, regardless of the fact that these guys did the task more times than these other guys, okay? Second result, better pattern matching abilities helps. So this is actually quite a strong result. We replicated this particular result many times. So this simply says that those that have that score low in the Raven progressive matrices test perform worse in this task than those that score high from the very beginning, okay, and consistently, and the effect is large. What was learned? So this was, to me, the most interesting, insightful result. So what we did is we calculated how much each decision that people made fit particular heuristics in the task. In this case, this is the results for the time heuristic. That is, if you were to just follow the deadline exactly in the task, what decisions you should be making, and then we compare that to decisions that people actually made. And we calculated a fit of the heuristic, okay? And what we see in this case is those that perform the tasks slowly, that is those that perform better, reduce the use of the heuristic, or their decisions fit the time heuristic less and less over time, okay? Those that do the task fast actually follow the heuristic about 62% of the time overall the course. They never reduce the use of the heuristic, okay?
Sorry,
Yes.
from a non-specialist, I mean, those were using gut feelings.
I'm going there. Gut feelings and experience are relatives.
Yeah.
So, yeah, that's right. So, pattern matching ability, to me this was also very interesting result, where we basically classify people that did very well in the pattern matching Raven test and people that did poorly in the Raven matching test. So you see that those people that score high in the Raven follow this idea, that is, they reduce the fit to the heuristic over time, less and less, regardless of the pace, okay? But for low Raven, the result was really interesting. So for the fast, those that were in the fast condition, they increase the use of the heuristic over time. For the slow, they decrease the use of the heuristic over time, okay? So the pace, the slow pace, helps the low capacity people perform better over time, okay? That's the main results. So to me, those were very insightful to come up with a theory that we call instance-based learning theory. Essentially, we found out through these experiments that we adapt through recognition. That's one characteristic. That is, we identify typical situations and responses. We look at the similarity between current situations and past experience. And then we use that experience. That is, we acquire context-specific knowledge, and that's demonstrated by the reduction of simple heuristics over time. Many people told me, well, maybe they are using more complex heuristics. We use combinations of many different heuristics, and it was never enough to explain the behavior. It was always a reduction of the heuristics over time, regardless of the complexity. It is true that the more complex, the less that reduction is, but this simply tells me that people are using the context-specific knowledge. They are using their experience. So that's where the decision theory came about. And long time ago, 1961, one of the first researchers on dynamic decision making said that static decisions theories have only a limited future. Human beings learn, and probabilities and values change. So these facts mean that the really applicable kinds of decision theories will be dynamic, not static. That was in 1961, and it's truly sad that dynamic decision-making researchers have been concentrating on a linear view static decision-making processes. So this is how most economists, psychologists, and everybody that studies decision-making sees decision-making. It's as a linear view, where we have essentially options, and you have probabilities that result in those options, but they don't change over time. So it's usually a one-shot decision-making problem, and given the same individual in the same conditions, they are expected to perform the same way. That is, the variability of individuals is also rarely taken into account. So anyway, there is years and years of research in this type of decision-making. So as an outsider of decision-making research, when I first came to my department, I had no idea. You know, I had done my dissertation on decision-making, but I really had no idea of this. I figured that decision-making was more like this. That is a type of situation in which we observe our environment, we search for alternatives, and we judge the goodness of those alternatives, and we make choices, and then we learn from them. So in my view, that was the only way we could make decisions. So I learned when I came to my department what was a traditional view of decision-making. So I call it as a closed loop, and I call this an instance-based learning theory. It's explained in this paper in 2003, but essentially involves a closed loop of recognition, judgment, choice, and feedback, and is seeing decision-making as a learning process. Now, at that time, I also was quite inspired by John Anderson. So John Anderson is a cognitive psychologist in Carnegie Mellon that developed a cognitive architecture called ACTAR, for acting rational. Essentially, it's a theory of cognition that is also implemented into a computer program. And the goal of a cognitive architecture is to encompass a lot of mechanisms that the human mind has into a computational form. Okay? So in 1998, when I first came to CMU, I actually took John Anderson's course, and I learned to do cognitive modeling. ACTAR has evolved. Has anyone here heard of ACTAR before? Okay, it's new, so wow, okay. ACTAR has actually evolved into a very complex theory. So my simple mind tells me that I should stick to the simpler theory. And the way I like to see ACTAR is as a 2x2 presentation. So ACTAR has a way to represent memory of two types, declarative and procedural. So this is not news for anybody that knows anything about computer science, so this is rules and facts. And also represents this information into a symbolic and a sub-symbolic way. A symbolic way means the actual representation. So for example, in the case of procedural memory, rules. If this condition occurs, then do this action. In the case of declarative memory, declarative facts. The chair is black, okay, chair, black. And the sub-symbolic level is actually a set of mathematical representations of how this information is processed, all right? So when I did the work with that task, the WPP task, I wanted to do an ACTAR model. And I didn't imagine how challenging that task ended up being. So I use mostly the declarative part of ACTAR, but I use essentially all the mechanisms of the theory, which are listed here. I'm going to go in detail in some of those, not now, but later when I present a simpler model. But this is so that you understand how the mechanisms are linked to a mathematical representation which describes the way humans behave through many years of experimentation. So anyway, once I got to that place, I figured that the problems people face when adapting to dynamic environments are really beyond the complexity of the task. That is, if I were gonna continue working on this WPP task, I would never convince anybody that these are the generic characteristics of dynamic decision making. So I felt that I needed to simplify that WPP task quite a lot. And I wanted to demonstrate that a single model, in this case instance-based learning, could accomplish multiple dynamic decision-making tasks with the same mechanisms. Some of you, if you are in modeling, you probably know that people say that we use our models as we use our toothbrush. You want to use only yours, you don't want to use the other person's. So I wanted to really demonstrate that this model was applicable to a variety of tasks. So that's when I started to reduce the complexity of the task. And if there is a lesson I've learned through these years, is that simplicity is very important. So being able to simplify our tasks in a way that we can explain them better, in a way that we can understand them better, is extremely important. So I did that through the years. I started with this one, and then I went to this one. I don't know how many of you have heard of the beer game. It's a supply chain management task, but in many ways it's a control task, and it's very similar to this task, but it's much simpler. And then I went to this, which is the simplest possible. So from, say, 20 times, I went to 10, and then I went to 1, right? And in all of them, I figured that people have problems figuring out the way to control for these systems, even in the one tank task. This is a task, by the way, that was converted by one of my students into a CO2 control task. Where he figured that this task could represent the CO2 accumulation in the atmosphere, that the inflows could be the emissions, and that the outflows that reduce this accumulation could be the absorptions. And then he brought a realistic model of the absorptions into this system and trained participants or figured out how humans did emission decisions. Anyway, that's just an idea of how this task was used for a naturalistic problem. And then I went all the way to the most simple way of representing any task, which is in a graph. So this graph, you can think of this of anything. This is just an example. You can think of water in your bathtub. You can think of people in the store. It's an accumulation type of task. So what you see in this graph is over a course of 30 minutes, you see people entering a department store, okay, and people leaving a department store. So this is the rate at which people enter and leave a department store, and we ask 4 questions. The first question is, during which minute did the most people enter the store? The second is, during which minute did the most people leave the store? Anyone for the first question?
4.
4. Anyone for the second question? Just yell at me, that's fine.
20.
Huh? More or less, it doesn't need to be exact accurate. So
21. Yeah.
I'm sorry?
Yeah, 21.
1?
21.
21, okay. All right, yeah, correct. So that's easy, right? Because you look at the graph and you look at the maximum number in the graph. Doesn't need to be exact. We actually did it with plus or minus 1. And then you look at the other graph, you look at the maximum point, and we did plus or minus 1. 96% were correct and 95% were correct. And these results in particular are from MIT graduate students in the School of Business. And now we asked two other questions. The third one was, during which minute were the most people in the store? When was the store fullest? Okay? During which minute were the fewest people in the store? When was the store emptiest? Emptiest, yeah. Anybody for the third one? 8. Anybody for the fourth question? 18. Okay. Both of those are wrong. Okay. But don't feel bad, because both of those are the most common answers. So this is a correct answer. That's when the store is the fullest. Why? So if you just think in terms of inflows and outflows and accumulation. So before this point, there is more people entering the store than leaving. What is happening to the people in the store? It's increasing, right? After that point, more people are leaving than entering. What is happening to the people in the store? It's getting lower and lower. It's emptying. The store is emptying. So the correct answer for this one is 13, plus or minus 1. And only 44% of graduate students in MIT Sloan School of Business answered this correctly. During which minute were the fewest people in the store? So you do have to consider the area in between the curves, and then you realize that there is more time. Well, actually, let me show you. 31% did that correctly. Those are the two most common errors. And this graph represents here the accumulation, the actual accumulation. Okay? So the answer to the last question is the last time period, the 30th. That's when the store is emptiest. People put all sorts of explanations as to why they couldn't answer that question. For example, well, I didn't know how many people were in the store at the beginning. That's a very common excuse. The reality is you don't need to know how many people are in the store at the beginning. That's not relevant for the question, right? You only need to base your answer on the information that you are given. And the information that you are given shows this stock over time.
Sorry, can I
Yes.
ask, when you asked that, they were first given the first sample?
The first two questions and then the last two, no, they were randomized.
Okay, so people didn't, so there is no correlation between answering first the first and then
No.
the second?
No, questions were randomized and are usually randomized. Okay, but indeed there is something in the questions, right? So we said, okay, how about if we ask them to draw the accumulation, all right? And furthermore, we determined that we need to look at the complexity of the relationships between the inflow and the outflow. So imagine the same department store, but now you have this leaving and this entry. What is going to happen to the department store? It's going to get fuller and fuller and fuller, right? So there's always more people entering than leaving the department store. So then we asked people to actually draw the shape of the accumulation of the people in the store over time, okay? And we did that over relationships that were from simpler to the more complex. And what you see here is this is what we provided people, this is the correct answer, and this is the most typical answer.
Wow.
Okay? So look at the simplest one. Okay? This is the correct answer. This is the correct answer, this is the most typical answer. Do you see a pattern here? What are people doing? And as you see, the more complex it is, they are copying, they are pattern matching, they are looking at the input and thinking that the output should look like the input. That's what people are doing. So what we saw is that the more complex it is, the proportion of people that follow the pattern matching heuristic or correlation heuristic, whatever we called it, is increasing. So the more complex the relationship is between inflow and outflow, the more they rely on this idea that the pattern of the accumulation should look like the inflow. Okay, so these are problems. These are problems, very basic problems that humans have in adapting to dynamic systems. Linear thinking, they make choices expecting that the effect will be linearly related to the cause. And misperception of feedback, humans select actions through reinforcing cause and effect loops over time. I still have time, right?
Yes.
Okay. All right, so the other way I simplified things was in choice. So you saw that in the very WPP task, in the very first task, there were many possible choices that could be made. So I figured that bringing that down to the most essential elements of choice, which is binary choice, would also be a good way to go. In particular because economists and psychologists, mostly economists, have been using these type of problems, gambles, to study choice. So those are gambles that we call from description, where you get an outcome, money and the probability. So if you see this, economists say, we calculate the expected value of these two, and then we choose according to the expected value. So which one would you pick, A or B? So A has higher expected value, you should pick B if you are rational, right? So I wanted to figure out how people do it from experience, and following on work on the decision-making literature, particularly an effect that was found in 2004 called the description experience gap. I looked at how people make decisions when they are experiencing those outcomes. So if you have two buttons, and one button corresponds to this, the other button corresponds to this, and you just click on the buttons and see the outcomes, what would be the result? What people found out, particularly Harvard, Erev and all, they found out that there is distinct, very different patterns of choice when you make decisions from experience than when you make decisions from description. When you make decisions from description, you actually underweight the probability of the overweight the probability of the red event. In this case, it's the zero. So that is, you think that the zero is gonna be more common than it really is, and then you move and pick the B. That's what prospect theory says, okay? But in experience, they found exactly the opposite, that you underweigh the probability of the red event. And that psychologically makes a lot of sense, because you are gonna experience a zero very infrequently. So you are gonna think that actually happens less than it really does, and you end up being more accurate when you do decisions from experience in this particular case. So, because I wanted to demonstrate that my theory, the instance-based learning theory, applied to multiple tasks, I thought that this could be a good task to demonstrate that. So we reduced that model that you saw in the WPP task with all those mechanisms to this most simplest version of that model. The most simplest version of the model says that each experience that we have has a value that is called activation, that comes from actar. Activation simply is a measure of how readily available a piece of information is in our minds, okay? And it depends on the frequency with which you have experienced that outcome and the recency. And those are presented here in this term. So this represents the frequency of experience, the time at which an outcome is experienced, and this D parameter is the recency parameter. The longer it is that you have experienced that, the lower is going to be the probability of retrieving that information from your memory. You're going to forget, essentially. So this is a forgetting equation or function. And then in this case, this is the noise. So we added only two parts of the activation equation. In actar, it's a huge equation. It accounts for pattern matching, it accounts for similarities with other elements, many other things. So because this is a simple task, I wanted to start with the simplest possible mechanism. So frequency, recency, and noise are the essential elements of this model. Those determine the probability of retrieving that outcome from memory, and then that is used in a mechanisms that we call blended value. If you see this is very similar to something we all know, which is expected value. So we essentially multiply the observed outcome by a probability, but instead of being the objective probability, this is the cognitive probability, which is calculated according to activation. And that's it. That's all that model is about. Okay. The power of this model has been demonstrated in many tasks, in many problems. This is one of the demonstrations in 2012. And what this graph shows is many gambles, and it shows the observed, which is the dotted line, and the IBL prediction, which is the black continuous line. Okay? In the majority of the problems, the model is doing quite accurately compared to humans. Okay, but again, coming back to the change, in this case, all the problems, all the gambles stay the same over time. They had the same probability, never changed, the outcomes never changed. Yeah, the problems are stochastic, but there was no change, okay? So I wanted to demonstrate that first the model was able to also capture the change, and I wanted to figure out how humans would adapt to the change in that simple problem. And there are many things that we can change even in that very simplistic problem, right? We can literally or most essentially change the probabilities and the outcomes over time, right? But we also can change the number of options. Why 2? What if I have 3 all of a sudden? We can change the information, we can change the feedback that is provided, the attributes. There's a lot of stuff that one can do in this simple setting. So the very first thing we did was we took Racco and Myler, 2009, data. And we didn't run in this experiment, we didn't run experiments. We got, well, at least not for this one, we got their data, and their data involved 2 options. And what is shown here is the probability over time of those 2 options, so getting a particular outcome. So one option was stationary, and that stationary option gave you plus 10 with 0.7, okay? Otherwise minus 20. And the other option was non-stationary. It gave you plus 10 with 0.9 up to this time, and then it decreased the probability and then got again flat. Is that clear? Okay, so they define these gambles with different types of changes over time. And all we did was to use our model out of the box to predict this behavior in these gambles. And what this shows is the IBL model and the data from Racco and Myler plotted over time. And this is the rate of the non-stationary choices. The model just is right on target in several problems. And this is not a fit to the data, this is a prediction from the model. Okay, now what we learned from that is that what are the effects of memory, which is what the model represents, right, for adaptation. So we learned that in static environments, the other environments we have run, longer lasting memory, that is the low D parameter value, may be a good predictor of the future outcomes. But in dynamic environments, high recency, okay, or high D parameter is more accurate in representing the future behavior. Okay, so that was something we wanted to follow on. And I think this is probably going to be the last study I'm going to show. So what we did then, based on that observation, is to think of decisions from experience in groups and individuals. Because groups presumably, or that's what we think, that groups together can think better, right? That we have a better memory, that we can make better mistakes, that we can coordinate and collaborate in groups, and performance could be better if we work in groups than individuals. But we suspected that exactly because of that reason, because of the group memory that could be better than individual memory, they would do worse in adapting to changes in the environment. So that's what we did. This is an this is a memory and cognition paper in 2014. So again, we use these problems, definition of these gambles. As you can see, there are different ways in which the options change over time. The dark one is the stationary, the other one is the non-stationary, and you see that at the beginning the stationary is worse than the non-stationary, but there are other problems, these two in particular, in which the stationary is better than the non-stationary at the beginning, right? And then it changes. Okay, so jumping directly to the results, this is results from experiments, and this shows groups and individuals, and shows the proportion of maximization choices, okay? So you notice in these problems that here this is the better option, and then after this time, this is a better option. So people need to learn that and notice that and then switch their options. So you can see here the proportion of maximizations, and what we see in several problems, not in all of them, is that groups are better than individuals before the change. But they don't adapt as well as individuals after the change, okay? We also notice that individuals explore more than groups do. So what this is just a measure of switching between the two options, which is our measure of exploration. And we see that individuals continuously explore more than groups, okay? And then we made predictions with the IBL model in both individuals and groups. This shows the human data against the IBL model, now in light gray. And the model is able to predict more, I think individuals better than groups, but still the pattern is very similar. Finally, what I think is important is the conclusions from the parameters. So here you see the best fit to the groups and to the individuals. And you see this is the best fit parameter for all the groups. You see that the D parameter, the decay is lower, and the noise parameter is lower than in individuals, okay? So that means these groups have better memory, no doubt, but that's hurting them for the adaptation. Individuals have worse memory in the sense that they can only remember the most recent information, but that's helping them for adaptation because they are exploring more. Yes?
Would it be correct to rephrase the thing in different terms, that is in terms of inertia? So maybe groups of, it might not be about memory, but about the inertia.
Yeah, absolutely. So in fact, in our paper, we discuss the issue of routines. And how in groups you tend to develop routines, and in fact we saw that by observing how the groups were behaving. So yeah, absolutely, I think that's a way to present it or explain it too. Anyway, I think I am over time. Perhaps I could go over the last part, but maybe that's I'll leave it here.
We have about 5 minutes left. Maybe we should take some questions around it off, if you wish. So. Yeah. So, any questions here? Well, okay. Yeah.
So I think it's exciting and very interesting. But can I try to be a bit out of the group question, right? So what? I mean, it's not. I mean, it wasn't. From what I heard, something I would have expected. The fact that groups behave in a way that are typically more, less reactive. Right? So perhaps I won't be able to quantify it, but somehow I would expect a behavior like that. So what are we learning that we didn't know? For example, I also appreciate the fact that working under stress or stressing people under stress doesn't seem to actually teach much, right? So I don't understand.
Well,
So what is the real breakthrough? It also, I read this book by David Kahneman about thinking fast and slow, and there is also, there are many other variables entering into the game, like what is perception of richness as a first son. So what is the final goal? I mean,
So, first of all, I don't think that is that obvious that groups perform less well or adapt less well in particular than individuals. In fact, here we are saying that they are actually better than individuals. So the comparison of individuals and groups is not that straightforward. But I think most interestingly, I think this can help us figure out what are the interventions that we can have in groups to help them do better.
So let's say that this is a university, and tomorrow morning we're going to be the top 10% of the world universities. What do we need to do?
Yeah, well, one of the things is diversification.
Yeah,
So,
exactly.
as you saw, based on exploration results. So one of the things is enforced exploration. So that's, one straightforward answer.
I totally agree. But that's something I knew. So I would like to understand what I didn't know.
So
what
why don't we do it then? So I think
we're doing it, but again, there is also, as you said, it's a group effect, which is very hard to change. Right? There's a group thinking, there is direction thinking, there is applying for grants as a person, that also has its own positive and negative effects. So the question is, if this is the way to go, and should be clear, can make people see the light? I mean, what does it take?
Well, it's our work as academicians to help in that way. Yeah.
So it's, and also, well, for example, I'm a theoretical physicist, so I know very peripherically about all this stuff. And we will actually, even in our groups, very much welcome understanding better this stuff, because we can also get better. So, but actually, we know very little about that. So in that sense, how do we gain access that outside the, the academic world? So this is something that I don't know.
Yeah. Yeah. Well, I think the people in organizational behavior are better equipped than psychologists like me to do that, because we do look at the the acute memory effects, like the one on how you remember information would help you, right? So let's say that we are going to design an intervention for an organization. You could think of ways of increasing the exploration by highlighting the most recent information, which is going to help in adapting to a change. Of course, if you can predict the change, that also would be good. But in all these cases, the main question is you don't know when the change is going to happen. So it's how people learn from the change. So I think, and in fact, I had nice conversations this morning. I know very little about organizational learning, for example, and I know that there are lots of parallels between individual learning and organizational learning. So perhaps we could make a higher impact if we have that type of collaboration.
Meanwhile, if I may, I also have a question here. Actually, so one is, what happens at the individual level if you increase the rate of change? One could, by extrapolation of your results, think that if you have a world where change happens faster and faster, people will become more and more, shall we say, myopic. Care more about, the present
Just the
day.
most recent, yes.
Yes. Or if you wish, their discounting increases in a different kind of way.
Yes.
So is that something you have looked into, or?
Yeah,
It seems to be happening, but that would be very interesting to know more about that.
It's unfortunate I didn't have time to go through the last experiment, but in the last experiment we actually asked for people's awareness of the change. That is, we explicitly asked them, did you notice any change in this task? And if so, when? Was it at the beginning of the task, in the middle of the task, in the end of the task? And then we separated people according to their awareness of the change. And we saw how awareness has reflects in the proportion of maximization as well as in the exploration that they do. The direction of the change matters a lot. So, for example, in this particular task, we had the non-stochastic option increasing over time or decreasing over time, in a way that at the beginning, the stochastic, the non-stochastic option or static was fixed, was better than the other one. And over time, the non-stochastic became better. So what happened in that case is that people's memory got stuck with the primacy effect, essentially, with whatever was better at the beginning. And they were unable to adapt to the change compared to this other one in which the non-stochastic was already good at the beginning, and they were able to detect the change because they were already making that decision. So all this is based on maximization. So people do look for better outcomes, right? So I don't question that general principle. We do look for better outcomes, but we are boundedly rational, like Herb Simon said, right? So we can only maximize according to the abilities of our memory in the constraint of the environment.
Okay, thanks.
Yeah, thank you.
If people base their decisions on faulty pattern matching, can we teach them to do better? I mean,
Yes.
if we elect people that install some response that we think is a linear
Yes.
response is needed, and we don't really listen to it, like in the climate change, experts say, listen, that we need to reduce CO2 levels, and people think when we flatline the CO2 emissions, we're good. No, we're still pumping out too much. Flatlining is not enough. We need to reduce. A discussion of vaccines where people don't trust experts and so on. Can we teach
Lovely
people?
question. I really like that
Can we
question.
teach people to
Yeah.
become better, or can we make them trust experts? That seems
Absolutely.
to go
We have the
downhill these
power
days.
of it. The power is the experience that we provide them through simulations. We can do that, of course.
So have you
right?
done experiments where you get opinions of others or from experts to reflect on when you make choices?
I have done experiments with the experts, but not perhaps in the way you are putting it so clearly. I think we can, we have the power to manipulate people's experiences. That's absolutely right. In whatever direction we want, you know, so that can go the wrong way too. But through simulations, we have the power to insert the instances that we believe will result in certain, in the results that we want to see, right? So the very first experiment that I presented from 2004 has those ingredients, but it wasn't with experts, and it didn't show an impact in the naturalistic
The
world.
learning part I saw when you repeated the experiment, but we have now, should we go to war in this country, should we reduce this kind of pollution? These are all new questions, and you can't have ordinary people look into all the details, so.
Yeah, and you're right, and working with experts is very challenging too. So for example, I'm working with cybersecurity experts now, and that's an area that's extremely challenging because it requires a lot of technical knowledge. We cannot just run an experiment like this. It's irrelevant for experts, right, to run an experiment with out of context options. But also we cannot run experiments that present a complex context with students at the university. So as academicians, I have to deal with those issues all the time, you know. Do I make the task more relevant for the experts, and then I cannot use my students, and I don't have the end that my reviewers require, right? Or do I do it simple and sort of make extrapolations to the experts? And I often choose the second route simply because I'm in academia and I need to produce papers.
Last question. Okay, so the good news, or even better news, is upstairs we can continue this discussion, because once you are done here, you go out of this door, turn left, there's a little staircase, and there'll be a bit of snacks and some drinks. So thank you so much for
Yeah, thank you. Thank you.
joining. And Cody, we have this one, and then